Edexcel Pure Core, Hyperbolic Functions 2, Inverse Hyperbolic Functions. 2.1, looking at inverse hyperbolic functions. You've previously seen that the inverse of a function can be found by reflecting that function in the line y equals x. So here we can see y equals sine x has been reflected to create the inverse function y equals r sine x. The inverse of sine x can be written as r sine x, or you can see it written as sine minus 1 of x. X equals f of y is a reflection of y equals f of x in the line y equals x. So the x equals f of y is a reflection of y equals f of x. And this idea will give us an algebraic way of finding an expression for r sine x. So let's look at the inverse of sine x. So let y equal r sine x, and that implies that sine y must be x. If we now write sine y in its definition, exponential definition, and if we multiply through by 2, we get 2x is e to the y minus e to the minus y. And if we multiply by e to the y throughout and do a little bit of rearranging, we can turn this into e to the 2y minus 2x e to the y minus 1 equals 0. And this is a quadratic in e to the y. Slightly unusual in the fact that the coefficient of e to the y is minus 2x, but it is a quadratic in e to the y. We could use a quadratic formula. I'm going to complete the square. So I'm going to write this as there's e to the y squared, so there's e to the 2y. To get the term in the bracket, you halve the coefficient of e to the y, so that is minus x. We've created a minus x squared, which is a plus x squared, so we take off x squared before we take away 1, and that has completed the square. So e to the y minus x squared can be written as x squared plus 1. And if we just consider both square roots to start off with, we get plus and minus the square root of x squared plus 1. Therefore e to the y is x plus or minus the square root of x squared plus 1. However, if you think about the square root of x squared plus 1, that must be a little bit bigger than x, which means that x minus the square root of x squared plus 1 would give us a negative answer. But we know that e to the y has to be positive. So we can dismiss this negative answer and say that e to the y needs to be x plus the positive square root of x squared plus 1, and therefore y equals the natural logarithm of x plus the square root of x squared plus 1. And y was, of course, originally r sine x. So that is the standard logarithmic form of r sine x. So the key things here when we're considering r sine x is to rewrite it as x equals sine y, which allows us to use the definition of sine y. Then we can create this quadratic in e to the y, which you can solve with a formula or completing the square. E to the y is of course positive, and therefore this negative result can be ignored. If we now consider the inverse of cosh x, so this is the graph of r cosh x here. In order for cosh x to have an inverse, it needs to be a one-to-one mapping. So the convention in order to find its inverse, is to take the x is greater than or equal to 0 side in order for this inverse to be defined. And again, r cosh y equals r cosh x has been rewritten as cosh y equals x, followed by the definition of cosh y, and then we can create this quadratic in e to the y. Completing the square gives us e to the y here, and we get y equals the two possible answers, ln of x plus the square root of x squared minus 1, or ln x minus the square root of x squared minus 1. We've got to take a good look at cosh x, because although there are two possible answers to cosh x equals a number, so say cosh x was 4, for example, cosh x equals 4 would give us two possible answers. But because r cosh is a one-to-one mapping, then we can only have one possible value for r cosh. And therefore, since r cosh x has to be positive, then the only logarithmic form we can take for r cosh x is ln of x plus the square root of x squared minus 1. If we now look at the inverse of tanh x, which is artanh x, we can see that artanh x and tanh x are mirror images in y equals x, and we can also pick out one or two other interesting details. For example, when x equals 1, we're dividing here by 0, therefore x cannot be, this function isn't defined when x is 1, and when x equals minus 1, we're doing the logarithm of 0, which is undefined. So artanh x cannot have values of 1 or minus 1. And indeed, that's where you will find the asymptotes on the graph. There's an asymptote at x equals 1 and at x equals minus 1. So all three of these logarithmic forms of r sin x, r cosh x and r tanh x will be in your formula book, and the values of x for their validity will also be stated. Notice that r sin x is valid for any real value of x. So now we can use these inverse functions. For example, if we wanted to solve 2 cosh x minus 6 is 0, then we could rearrange this to cosh x equals 3. And just before we go on to solve this, if you just consider cosh x equals 3, so there's cosh x, or a sketch of cosh x, and we want it to equal 3, we can see that there should be two solutions for x, a positive and a negative one, which is symmetrical about 0. That's worth bearing in mind as we use the logarithmic forms. So if cosh x equals 3, then x is r cosh of 3, and using the logarithmic form of r cosh, x is the ln of 3 plus the square root of 3 squared minus 1. So x is ln of 3 plus root 8. However, we know that there must be a negative answer as well. So we could get that by using the previously dismissed version of the logarithmic form. So notice that cosh x equals 3 will have two solutions, and by writing it as an inverse function, so here we've gone for the cosh minus 1 3 notation, we can write this as a logarithmic form. We can use the positive root of 8 or the negative root of 8, or if preferred we can say that x is plus or minus ln 3 plus root 8. They are indeed equivalent. So in the next session we're going to be looking at differentiating inverse hyperbolic functions.